Hello, Astronomy. Mr. Janowski here. Here's the next part of the Chapter 2 slides. So do now, what is parallax? Parallax is the apparent shift in position of foreground objects compared to background objects when the observer moves. So this is that thing where if you hold your thumb out in front of your face, look at it with one eye, see what it blocks in the background, and then you switch eyes, your thumb appears to move. So it is apparent motion. And this is a useful thing in astronomy. Question 2, what is retrograde motion? So looking at that bottom picture there, retrograde motion is this apparent movement where a planet that usually night after night seems to go west to east will temporarily slow down, stop, go east to west for many nights, then slow down, stop again, and then go west to east again back in its normal path. So a very confusing thing. Why do the planets seem to do this? This is of tremendous interest to the astrologers among you. So yeah, why does this thing happen? So, who created a geocentric model full of epicycles that dominated astronomy until the 1500s? That would be Ptolemy. So, Ptolemy, the whole point of adding the epicycles was to try to explain the retrograde motion. So, that's why he did that. So, Ptolemy had a system that kind of worked and could kind of predict when you would get the epicycles, but it was extremely complex. You had circles upon circles upon circles, and it kind of violated this idea called Occam's razor. So, what is Occam's razor? It's the idea that the simplest explanation tends to be the correct one. So if you have two different theories that both pretty well explain what's going on and make pretty accurate predictions, which one of them is actually correct? It's going to tend to be the simplest one. And finally, who was it that reintroduced a heliocentric model in the 1500s that revolutionized astronomy? That would be Copernicus down there at the bottom. So he didn't introduce it originally. Aristarchus is, the guy we're giving credit for. Aristarchus, the ancient Greek, the first person to have a heliocentric model, but nobody believed Aristarchus at the time until Copernicus came along, 1,500 plus years, about 1,800 years later, really, and looked at Aristarchus's idea and kind of brought it back. So back to Copernicus. So Copernicus, his main thing is that he brought back heliocentrism. So he is the first modern heliocentrist astronomer. So this isn't the only thing that he did, though. Using his heliocentric model of the solar system, he was able to do some geometry, measure some angles, and figure things out. And he figured out the relative distances from the sun to all of the planets. Now, he couldn't figure out the absolute distance of any of this, any of the distances from the sun to the planets, but he could figure out the relative distances, meaning how they compare to each other. And so he did it by comparing them to the distance from the Earth to the sun. And that's a very useful unit in astronomy called the astronomical unit. So the distance from the Earth to the sun is 1 AU, 1 astronomical unit. So if you look at this table here, these are the actual distances from the Earth to the given planet in units of AUs, astronomical units. And if you compare Copernicus's calculations to the actual, modern accepted distances, Copernicus did really well. So yeah, good on Copernicus for this. So he had all these things, pretty well figured out. Now he didn't know the absolute distance to any of them because he didn't know what, the actual distance. What is an astronomical unit? It turns out it's about 93 million miles or about 150 million kilometers. He didn't know that. He was just calling it 1 AU. And so he figured all this stuff out. So yeah, good on Copernicus. Now, Copernicus published all of his ideas in this book called On the Revolutions of the Celestial Orbs. Now, he was well aware that the church wasn't going to like this book, and that this book would cause quite a stir and would possibly get him into trouble because the church really liked Aristotle's model of the universe, and the church really liked the geocentric model, the model that put the Earth at the center of everything. So that really fit in with Catholic doctrine pretty well. And taking the Earth out of the middle of everything and making Earth kind of not the point of the solar system, and Earth is now no longer the point of the universe, that was upsetting to the church. They weren't going to like it. So he was smart. He waited until he was on his deathbed to publish it because he knew that, he was about to die anyway. So yeah, go ahead and publish it. And once you're dead, they can't get you anymore. So that's what he did. So he published this, and his main idea was basically correct. However, some of the criticism that was going to come raining down on now dead Copernicus about this book, some of it was actually justified. Um, the great thing is, again, it explained retrograde motion with a heliocentric model in a way that was much more simple than any geocentric model could. So the geocentric models all had epicycles and crystalline spheres and all kinds of crazy complexity in order to get them to agree with observation. So Copernicus's heliocentric model was much simpler. However, it wasn't actually any more accurate than Ptolemy's model. So why was it not more accurate? Um, it was not more accurate because Copernicus was trying to get this all to work using circular orbits. Um, and the orbits of the planets are pretty close to circles, but they're not exactly circles. They're slightly oval shaped, a particular shape called an ellipse. So, to sum up, the arguments against Copernicus: lack of perfect agreement with observation. So, his model, again, was much simpler than Ptolemy's, but it wasn't any more accurate because Copernicus was trying to make all this work with circles, and circles just weren't the exact right shape, and he didn't realize that. Also, there was a lack of observed stellar parallax. So that's why we started with parallax in the do now questions. People were saying, well, no, if the Earth is moving, then we expect to see parallax in some of the stars. The more nearby stars should show us some parallax compared to the further away stars. We look for that, we don't see it, so there's no parallax, so then therefore the Earth can't be moving. It's a good argument. It's not right because they had no idea how far away the stars were, but they were thinking at least. And finally, Copernicus's book disagreed with the teachings of Aristotle and the teachings of Eudoxus and the teachings of Ptolemy, and those ideas were all supported by the Catholic Church. And then finally, not to put too fine a point on it, Copernicus's model kind of disagrees with common sense because what Copernicus's model was saying, and what is true, and we all accept this now, is that the Earth is actually spinning very quickly on its axis, and the Earth is flying around the sun. Um, that's not readily apparent that those things are happening. It doesn't seem like we're spinning around here in Pennsylvania. It doesn't seem like we're flying 800 miles an hour to the east right now, but we actually are. And the entire planet is going around at tens of thousands of miles per hour around the sun. So that's totally true, but it doesn't seem that way. So, yeah, common sense was kind of on, the Ptolemaic and the Aristotelian model side, even though those things are both wrong. And then we get to Tycho Brahe. So I will put the link to this video on Tycho Brahe's life in, the description of this video. So yeah, if you didn't see this video, see this video. Tycho Brahe led a very interesting life. He was kidnapped by his very wealthy uncle at age 2. In his teens or early 20s, I forget when exactly, he got into a duel with a fellow nobleman who actually was his cousin over a math problem. And poor Tycho Brahe ended up getting his nose mostly chopped off. So he had to wear a fake prosthetic nose for the rest of his life. And then he inherited all of his uncle's money, started doing some astronomy, and having an affair with the Queen of Denmark. And the King of Denmark gave him like a whole island to set up this giant observatory on. This island observatory called Uraniborg. I think that's the name of it. Also, he owned a pet moose, which is crazy, but he had enough money. So if you have enough money, you spend it on stupid things. He bought himself a moose. The moose ended up dying because he lent it to a buddy of his to show off at a party. At the party, they got the moose drunk. The moose fell down the stairs and died. So very sad. And then finally, Tycho Brahe himself died from not peeing in time. He was at a banquet. He drank too much. Decided it would have been rude to leave the banquet to go to the men's room. So instead of doing that, he just sat there until his bladder burst. And then he spent the next 11 days in agonizing pain, and then he died. So, yeah. Tycho Brahe, interesting fellow. The key ideas for us, though, because this is astronomy after all, is what did he do in astronomy? His biggest contribution is he made much more accurate measurements than anyone else at the time was making. So He's called the last of the great naked eye astronomers, meaning he didn't use a telescope. He was just doing this with other kinds of instruments and lining things up and measuring angles and things like that, but not an actual telescope. But he was really good at it, and he made extremely accurate measurements. And he also figured out a couple of things. He observed a new star. So this is a nova. This is actually an old star that exploded. And he argued that because I don't see any parallax with that star compared to the distant stars, that thing must be really, really far away. Which, on the rare occasions when people had observed a new star before then, they didn't think it was actually all the way up there in the heavens with the stars. They actually thought it was in the atmosphere. And same thing, he saw a comet. Observed that, figured out it must be way beyond the moon because there was no parallax. And that means the comet must be really far away too, which was, again, surprising. So this sounds weird, but in, 1500s kinds of thinking, people were stuck with this idea that the heavens are eternal and perfect and unchanging. So therefore, you can't have any new stars, and you can't have any comets. They can't be out there in the heavens because that would be something changing. So people at that point actually thought that, these novas, which are fairly rare, and comets, which are a little bit less rare, when you see those things, those are just in the atmosphere. They're in the sky, but they're not way out there in the heavens. They're just in the sky. And Brahe proved that, no, those things are really far away. Those are actually up there, in the actual heavens. And the other thing is Brahe, so he knew of Copernicus, and he liked Copernicus's heliocentric model that put the sun at the middle, but ultimately he couldn't accept it because he said, well, there should be parallax. So again, people are stuck on this idea, well, if the Earth is moving, we expect to see parallax. We're not finding any, so therefore the Earth isn't moving. And again, there is parallax, but it's super tiny because the stars are really far away. But Tycho Brahe didn't know that. So Brahe is the one person who is not really a geocentrist, and he's not a heliocentrist. He kind of split the difference. He had this hybrid model. So according to Brahe's system, here's the Earth in the middle. The moon goes around the Earth. Okay, so far so good. The moon does go around the Earth. But he had the sun going around the Earth. So this looks kind of geocentric because the sun is in the middle. But he also thought, well, the sun goes around the Earth, but all the other planets, they go around the sun. So that is a little bit heliocentric. This is weird. This is a really complex model that really nobody other than Tycho Brahe ever believed in. This one never really caught on. It's just kind of the halfway point between moving from geocentrism to heliocentrism. So weird. And then we get to Kepler. So when Brahe died in the HRE, the Holy Roman Empire, he had an assistant named Johannes Kepler. So Kepler took Brahe's wonderful, wonderful data, and he started analyzing it, and he came up with 3 very important rules. So these are Kepler's rules of orbital motion. And first, he found that orbits are not actually circular. They're actually elliptical, which was surprising because people loved circles. Circles are the perfect eternal shape. So why aren't things doing circles? Why are they doing something else? They're doing ellipses. So how did he figure this out? He took Brahe's data on the motion of Mars going around, tried to get it to fit to a circle, and couldn't quite get it to work. And then he tried an ellipse just on a whim, and it worked. Turns out Mars was doing a perfect ellipse around the sun. So this is what an ellipse is. It's a very particular kind of oval with these certain properties. And Brahe figured out, do I have it here? Okay, I have it here. The sun is not at the center of the ellipse. So if you're looking at my cursor on the right ellipse here, here's the center of the ellipse. The sun's not at the center of the ellipse. The sun is at one of these other special points of an ellipse called a focus. So the sun is at one of the focuses. At the other focus over here, there is nothing. The sun is just at one of the focuses. And so he saw that the planets were actually doing ellipses around the sun with the sun at the focus of one of the ellipses. So this is Kepler's first law, also known as the law of ellipses. Planets move in elliptical orbits with the sun at one focus of the ellipse. So yeah, there's that one. So Kepler's second law, basically in a nutshell, says planets move faster when they're closer to the sun. So if you watch the GIF, the planet's moving very quickly. Now it's far from the sun. Now it's moving slowly. So yeah, that's the gist of the second law. It is also called the law of equal areas. because the idea is in any equal amount of time, as the planet does its orbit around the sun, in any equal amount of time, the planet will sweep out an equal area. So in the sun, going from December to January, from here to here, it's fairly close to the sun, so it's moving very quickly. So this backside of this, pizza slice right here is pretty big, but the distance to the middle is pretty small. So this sweeps out this purple area here. 6 months later, we're over here, May. Going from May to June, the Earth is far from the sun, so it doesn't move very far because it's moving very slowly in that month. But the slice that it's sweeping out is much longer. So now we have a long, narrow slice here. Over here, we have a short, stubby slice. But it turns out the area of this slice to this slice, it's the same. And in fact, all of these slices are the exact same area, even though they're very different shapes sometimes. So that's the second law, the law of equal areas. And then the third one is the mathematical one. So Kepler looked at the period, which is the amount of time it takes for a planet to complete its orbit around the sun, and he looked at the semi-major axis. So again, this is the semi-major axis. It's from the center of the ellipse to the outside of the ellipse along the widest part of the ellipse is the semi-major axis. So we'll call that distance A. The period is just the amount of time it takes the planet to do one lap all the way around the sun. So he realized there's a mathematical relationship to these things. So if you take the period squared and compare it to the semi-major axis cubed for all of the planets, and you plot them on a line, you end up with a line. So on the x-axis here, we have the orbital period squared for each planet's total time around the sun, measured in units of years. And over here on the vertical axis, you have the cube of the semi-major axis of the orbit. So you take that distance A, you cube it, you compare it to each planet's period of orbit, you square that number, and everything falls in a line. And in science, when you're graphing something and everything falls very nicely on a line, you're very, very happy because that means you found an important relationship. These things are in some way related. So this is the law of periods. You have that relationship between the period P and the semi-major axis A. P squared equals A cubed. So you can kind of see that going on here. So these are all of the planets going around the sun. So if you look at this blue guy right here, this is the Earth. So look at the size of the Earth's orbit. So kind of small compared to some of the other planets. And the Earth is moving kind of quickly. Now compare it to Saturn, which Saturn's very easy to see. It's the one with the big rings. So Saturn's going around. Saturn has a much bigger orbit that it has to do, and it's moving much slower. And the relationship to the size of the orbit to how much time it takes it to do its orbit is that relationship at the bottom. P squared equals A cubed. So that is Kepler's third law, the law of periods. So this slide, I'm not going to spend any time on it, but this will be useful when you're studying. This is just all three laws all together. The first law, the law of ellipses. The second law, the law of equal areas. And the third law, the law of periods. So there's also a quiz to do for the next class. And then at the end of class, we did a Kahoot. So there's that. So I'll put a link to the Kahoot in the description to this video as well. That was it for this part of the slides. Hopefully you found that helpful.